In this 16-3 lesson video, we're going to look at constructive and destructive interference of sound waves. And the first situation we're going to look at is how to find the constructive and destructive points along a straight line. So in this first situation, we have two speakers along a straight line. They're both in phase. They're sending out sound waves with the exact same frequency. And one's behind the other, and we want to know out at some point here, do we have constructive or destructive interference? Well, it all depends on the distance between these two speakers. If we want constructive interference to occur, we're going to learn that it's the difference between those two speakers is going to be one wavelength or two wavelengths or three wavelengths difference. Where if we want destructive interference, it would be the half wavelengths. So if we look at this picture here with the two speakers, we see that we're looking at constructive interference. You see that these waves are in phase, that the yellow wave here is in phase with that red wave on top of it. And so you're going to have constructive interference right here at this point. You have a crest meeting a crest, and so the wave's actually going to be louder, and you'll have constructive interference. In order for that to happen, you have to go back behind this. The second speaker has to be one wavelength back behind that first speaker in order for those waves to be in phase. But you could also be two waves behind or three waves behind in order for constructive interference to occur. So in this situation, if you want constructive interference, the equation for this actually becomes this right here, that the distance between the two speakers, delta D, is equal to some integer number of wavelengths, m being 0, 1, 2, and 3, in order for constructive interference to occur out at this point. Now, for destructive interference to occur, you can just imagine that it has to be a half wavelength apart because you want the waves to be out of phase. So in this picture here, we show destructive interference where we have these two speakers again. The sound waves are the exact same frequency. They're in phase, except this wave coming from that first speaker is going to be half wavelength out of phase with the second wave, or the second speaker. And you're going to have destructive interference out here at that point. Actually, you're going to have destructive interference all the way along, and no sound will occur. This is similar to what the canceling headphones do, the sound canceling headphones do that we wear. They read the frequency that's coming into the headphones, and they send out a frequency that is a half wave out of phase. Now, you can just imagine that it could be a half a wave, or 1.5 waves back behind it, or 2.5 waves back behind it in order for constructive interference to occur. And so our equation becomes this. It's half a wavelength. M could be 0, so it would be half a wavelength. And when M is 1, it's 1.5 wavelengths, and then it's 2.5 wavelengths. That distance D between the two speakers is some half wavelength behind that first speaker in order for destructive interference to occur. So now we want to know what happens if the two speakers are not in line. What if they're side by side and we're looking at these spherical waves that are going outwards? We want to look at what the interference of spherical waves are and how to find constructive and destructive interference points. This is a two-dimensional model, and so what we're going to do is not look along a straight line, but look at different points out here in front of the speakers to see where these interference points occur. So the sound waves from the speaker spread out in front of the speakers, move out forward in a spherical fashion, and they start overlapping each other. And you'll have this destructive and constructive interference. And the ideas, though, are very similar to the interference along a straight line. This shorter distance from this first speaker out to our point has to be, for constructive interference, it has to be one wavelength or two wavelengths or three wavelengths shorter. And then for destructive interference to occur, it has to be a half wavelength or 1.5 or 2.5 wavelengths shorter. So it's really the same idea, except these distances here have to be off actually by the same amount as we previously talked about. So in order for constructive interference to occur, the change in R, the delta R, that's the difference in distance between, we'll call this R1, we'll call this one R2, and so delta R is just R2 minus R1. The difference in those distances has to be some integer number of wavelengths in order for constructive interference to occur. It could be one wavelength apart or two wavelengths apart, and then what you'll have is a crest and a crest will meet at that point, or a trough and a trough will meet, and you'll have constructive interference out at that point. And as you can imagine, destructive interference would occur when they're half wavelength apart or 1.5 wavelengths apart. So for destructive interference, the change in the R value is, again, according to this equation, it's really, you can see it's the exact same equations as we previously had, just for a different situation. It's half wavelength or 1.5 wavelengths or 2.5 wavelengths to get our destructive interference. So what we have here is a simulation of a person listening to sound to a speaker. And so they'll just hear this regular tone. But what if we put two speakers in place here? What will they hear? So we'll look at this visually, and we'll look at a two source. We'll look at two speakers, and we'll see that the waves coming out of each speaker overlap, and we're going to get constructive and destructive interference. And if we enable the audio, and we move this person, you can find dead spots, and you can find loud spots, so you can see where destructive and constructive interference is occurring. The last topic we're going to look at is called beats. And what are beats? The fancy definition for beats are the superposition of two waves with slightly different frequencies can create a wave whose amplitude shows a periodic variation. So what that means is these two waves have slightly different frequencies, and they're going to start interfering with each other. And what happens is, at certain points, they have total constructive interference, and other points, they have total destructive interference points. And so what you'll hear is a wavering. You'll hear wow, wow, wow. You hear a sound get louder and small, and you get louder and softer. For those of you who play musical instruments, that's where you're tuning your instrument, and you're trying to get rid of that wavering sound, trying to get rid of those beats. So if we look down here at the picture, we can see there's these two waves here that are slightly off, have slightly different wavelengths, and so they start interfering. Here they interfere constructively, so you hear a loud noise. Then at this point they interfere destructively, so you hear a soft noise. And then again they interfere constructively, and you get this louder noise. And that's where that wavering comes from, that wow, wow. And another picture, another way of looking at that is with this picture here. This shows here that there's constructive interference right at these points, and in between there's destructive interference. And so what you see is this wavering. You see this wow, 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 wow. And so you'll hear this beat frequency. And in order to figure out what that beat frequency is, how many of those wavers you hear per second, all you do is subtract the two frequencies from each other. So if you have one sound that's 400 hertz, and another sound that's 402 hertz. The beat frequency is 2 hertz, and that means you'll hear two of those waverings per second, two of those beats per second. The beat frequency can be visualized here. If you look over on the left-hand side, you'll see here's a beat, a loud noise, and then a soft noise, and then a loud noise and a soft noise. And so you'll see that these two waves up above are interfering with each other constructively and destructively, and you get this wavering sound. You get this large sound, and then you get this soft sound, then large sound, then soft sound. So in this first example here, this person is standing in front of the two speakers, and let's say the distance here in front of speaker 2 is 5 meters. And if our wavelength coming out of the speaker, out of both of these speakers, let's say the wavelength that we have here is 1.5 meters. What you need to tell me is what distance here do we have? What is this delta D? So that we have constructive interference and destructive interference. So pause the video and see what you think. So here we have For constructive interference, our distance is m times wavelength. Remember, this has to be multiple wavelengths away. So since our wavelength is 1.5 meters, well, 1 times 1.5 is our distance is 1.5 meters, or it could be 3 meters, etc. And that's this distance here. For destructive interference, the delta D is equal to m plus 1/2 wavelength. And so if you have m equals 0, your delta D is half a wavelength, which is 0.75 meters, and so on. You'd have m equals 1, so it'd be 1.5 times 1.5, be 2.25 meters, etc. So let's do the second example. Here we have two speakers, and Sam is out in front here. And we want to know what R2 minus R1 has to be for, let's say it's constructive interference. And for constructive interference, we know that delta R equals m times wavelength. Well, we don't know what the wavelength is, but we can certainly solve for it. It's velocity equals frequency times wavelength. So wavelength equals velocity over frequency. So if we take our velocity of 340 meters per second and divide by our frequency of 170 meters per second, we end up with a wavelength of 2 meters. And we can go ahead and use this idea where delta R equals, well, 1 times 2 meters, or 2 times 2 meters. And so we have our delta R is 2 meters, or it could be 4 meters, etc. And so they said if R1 is 4 meters, then delta R is 2 meters, so the R2 has to be 6 meters long. And that would be constructive interference right there at that point. If it was destructive interference, we would then just do delta R equals m plus 1/2 times a wavelength. And we do the same kind of thing. We see that delta R would end up being, if m is 0, that's our first m for this, 1/2 times the wavelength is 1/2 times 2 meters, so delta R would be 1 meter. And in that case, instead of 6 meters, it would have been 5 meters, and it would have been destructive interference at that point. And the last one here, we have just a situation where we can say, all right, what wavelength do we have to have in order for constructive interference to occur? And that, again, is this idea of delta R equals m times wavelength. And just let's use m equals 1. Well, we know delta R in this case here is 1 meter. It's 9.5 meters minus 8.5 equals 1. So the wavelength in our case is 1 meter. If you want destructive interference, that would have been delta R equals m plus 1/2 times the wavelength. And so here we have delta R equals 1/2 the wavelength. And we know our delta R is 1 meter equals half a wavelength. And so in this case here, our wavelength is 2 meters in order for destructive interference to occur at that point.